Hello and welcome to notes on polynomial roots and identifying them, as well as the fundamental theorem of algebra like you see right there. First, the fundamental theorem of algebra just states, I want to highlight a couple things there. That if you have a polynomial function with degree n greater than 1, so the biggest power is greater than or equal to 1, there's at least one zero, and that zero could also be a complex number. In addition, that's all that corollary means. In addition to every polynomial function of degree of n greater than 1, so the highest power is greater than 1 or equal to, has exactly n zeros. Okay, so a polynomial function with the degree that says degree 3 has exactly 3 zeros. All right, that's just where the graph crosses the x-axis, things that make the polynomial 0. Okay. I just want to show an example of that. So if you look here, I've got a graph highlighted, x squared minus 4. You know that factors to x plus 2x minus 2. So in here, we have the degree of 2 for this polynomial. The highest degree is 2. You can see that our graph crosses the x-axis at -2 and at +2. Okay? So there are 2 zeros for this graph with degree 2. All right. And there's 3 types of zeros: rational, irrational, or complex. Okay, so for example, I'll stick with the x squared minus 4. Okay, those would be rational. Okay, you know that factors to x plus 2x minus 2. Okay, difference of 2 squares, right? And if we set this whole thing equal to 0, the whole equation, we're going to get x equals 2, x equals -2. Okay. Or just do it another way. Set this equation equal to 0, x squared minus 4. So set it equal to 0 here. X squared equals x squared equals positive 4 after you add it to both sides. And then x equals plus or minus 2. Okay, it's the same thing, right? Those are the same thing. X equals 2, x equals -2. X equals 2, x equals -2. All right. So point of factoring. You set it equal to 0. Okay, then you factor. Okay, those would be considered rational zeros. 2 and -2 are rational numbers, right? So the x squared minus 4 has 2 rational zeros, 2 rational x-intercepts, 2 x-intercepts, excuse me, 2 places where it crosses the x-axis. All right, let's go on to irrational. I'm going to erase a little bit to give myself some room. All right, an example of irrational roots. Okay, those are still real numbers, but they're irrational. Okay. Would be x squared plus, let me redo that one, x squared minus 5. So let me erase that. X squared minus 5 would be an example of rational. I got a little ahead of myself. Okay, so x squared minus 5 now. If we set that equal to 0, we're going to have x squared equals 5. And then x equals plus or minus 5. I'm talking about irrationals. X equals plus or minus 5 now. Excuse me, let me go back again. X equals, I have to square root, as I'm sure you already know. And we can't square root 5, so x equals plus or minus the square root of 5. Okay? So that's an irrational number, but we still have a positive and a negative square root of 5 there. All right? And of course, that can't factor. So that would be an example of irrational roots. This would cross the x-axis at plus or minus the square root of 5, okay, which is somewhere a little more than 2, so 2 point something. Okay. So I adjusted my graph to, as you can tell, to be plus 5 there. Or excuse me, minus 5, x squared minus 5. And you can see that my 2 irrational roots are 2 2 point something positive and negative 2 point something. Okay, somewhere around 2.2-ish. Okay, can't tell where that exactly is. 2.236 it looks like. All right. There you go. There's an example of irrational roots. Right, and the last possible kind of root would be complex numbers. In this case, x squared plus 4 would be an example of that. Let's go look at that. If I were to solve x squared plus, set it equal to 0 and solve, I would get x squared equals negative 4. Then when I square root both sides, I'm going to get x equals the square root of negative 4. Okay, hopefully by now you know that is x equals plus or minus 2i. Anytime you square a negative number, you're going to have an I, right? There's the complex part. Okay, you might be thinking, wait, how can you have an imaginary number, complex or imaginary root? Where would that appear on a graph? Okay, we'll see. I'll show you some examples of that. That just means if you think of a root as crossing the x-axis, if it's an imaginary root, okay, that means that root or that x-intercept is out there, okay, but not at the x-axis. It's on the graph somewhere. We don't know where. It's just not crossing the x-axis when it appears, okay? And you'll see what I'm talking about there coming up. All right, just a couple things to talk about real quick before we start graphing. Okay, irrational roots and complex roots always come in pairs. Okay? You already know I'm going to go down to complex first. Okay, you already know that complex roots have conjugates. Well, anytime, anytime you have a complex root, okay, this theorem says you then also have to have the conjugate. Okay, so you never have just a plus bi as a root, whatever that is. You're also going to have a minus bi as a root. All right. It's kind of why the quadratic formula is negative b plus or minus. Okay, because the quadratic formula takes into account that you have to have both. If you have one complex number, the positive version, you have to also have its conjugate. They will both be roots every time. Okay, and the same thing with the irrational root theorem. It's the same idea, only we're just talking real numbers, irrational numbers. Okay, anytime you have a plus, okay, the square root of something, if that's a root of your whole, that's the root of your whole equation, your whole polynomial, if that's a 0, then the a minus b square root will also be a 0 of your polynomial. Okay, that's all that's saying. They come in pairs. Plus or minus, that's a product. That's just the product of square rooting something. Okay, it's always plus or minus. Okay, so those roots will always come in pairs if they're irrational or if they're imaginary, complex. All right, we have this really unique thing called multiplicity when it comes to graphs and roots. Okay, sometimes a specific root or if a factor, okay, can appear multiple times in a polynomial. For example, x squared plus 2x or x squared plus 4x plus 4. If you were to factor that, you'd get x plus 2x plus 2. Both of those are roots of the polynomial x plus 2 and x plus 2, but they're the same number. They're both going to give you x equals negative 2, okay? So sometimes you have it's called multiplicity, where a root appears more than one time, okay? And there's some shortcuts as we look at graphs to figure those out. So when you have a situation like this where, hold on, I'm still on my, I'll erase what I just did. We have a situation, okay, like here, where the curve comes and I think of it as bouncing off of the x-axis. So it was coming up, and then bounces off the x-axis. Doesn't actually cross it. Okay, that's considered an even multiplicity. In general, multiplicity of 2. There's actually 2 roots there. In this case, it's negative 3. We have negative 3 is a root twice for whatever equation is making this graph. All right. It's a multiplicity of 2, or really, it could be 4 or 6 or 8, just an even number. Okay, there could be 8 roots to this polynomial, all at negative 3. This has to be an even number if it bounces off like that. Okay, when we have the other situation that you see on this graph, all right, so at the point 0, the graph kind of bends and crosses, but it only crosses once, then keeps going. That's odd multiplicity, all right? So that's at least 3 roots there at 0. And maybe more. Maybe it could be 5, maybe it could be 7, but that's odd multiplicity of at least 3, okay? Just things to keep in mind. If you need to replay me saying that, because I know that's a new term, you haven't actually heard of any of that before, you need to go back and watch the last 2 or 3 minutes of me explaining that. Do it again, okay? All right, we're going to have a little bit of graphing examples and learn some of the things we just learned about polynomials and their roots. So example 1, graph each polynomial. Identify the real roots and classify them accordingly and state the multiplicity. Okay, so let's look. We've got this equation x cubed plus 6x squared plus 12x plus 8 equals 0. And our first question says, using the fundamental theorem of algebra, how many total roots are there? Well, let's think back. I'm not going to scroll up. You can go look back. The fundamental theorem of algebra just says, whatever the highest degree is, that's how many roots there are. So the highest degree is 3. Thus, there's a total of 3 roots for this equation. Okay? We don't need to graph it to figure that out. The fundamental theorem of algebra already tells us right away. Highest degree on the variable, that's the number of roots. How many of those roots are imaginaries? Okay? This is where we actually have to start going to the graph. All right? So I'm going to flip over to Desmos. I've already actually got that graph up for us. There it is. Okay. I'm going to move my picture a little bit to right here. All right, there it is. So let's see if I can zoom out a little bit, make sure we're getting everything. So how many of these are imaginary and how many are real? So first of all, I've got that unique situation that we just talked about with multiplicity, okay, where it approaches the x-axis, it bends at the x-axis, but doesn't come back. This doesn't come back down like that. Nope, that just keeps going. Okay, it crosses once, and it looks like it crosses at the point, I don't know, 2. Let's see if we can actually get that point to pop up here. Yep, 0.20. All right. So negative 20. So yeah, there's multiple roots happening there. And if you remember, if it bends weird like that, it has to be an odd number of roots, the least of which is 3. So my guess is, since our equation has a degree of 3, all 3 roots are at that one specific point. Okay, which was negative 20, right? Let me just go check. Yep, negative 20. So all 3 of our roots are at negative 20. Okay. So how many of those are imaginary then? None of them, because they're all negative 2, so 0. And they're all rational, because negative 2 is a rational number. So there is 3, okay, that are rational. I think it wants us to probably list the actual roots here. In this case, it looks like it's negative 2. So there's 3 roots, all at negative 2. So x equals negative 2. I'm just going to write that with a multiplicity of 3. Multiplicity 3. All right, cool. And then, of course, none of them are irrationals. So NA. All right, awesome. All right, here's the next one. X to the 4th plus 8x cubed plus 18x squared minus 27 equals 0. Using the fundamental theorem of algebra, how many total roots? Right away, highest degree is 4. Yeah, you know that. We have 4 roots. All right. How many of those are imaginary? How many rationals? How many are irrationals? And what are those? Okay. This is where it gets a little tricky. I'm going to go back to Desmos. I've got a graph for us there. Okay. And look, we have kind of a unique situation again. Ooh, why is that moving? All right. Unique situation there. And then it crosses here. Okay, so I'm just going to make sure that those are the points -3, 0, yep, and 1, 0. All right, awesome. So at -3, I've got that bendy thing, which we know is the least multiplicity of 3. There's at least 3 roots on -3, 0. And then this one, just the 1, 0 just goes straight across the x-axis, okay, without bending or anything special. Okay, the curve remains smooth. So that's one root at the point 1, 0. Okay, so going back, the PDF, how many are imaginary? Doesn't look like any, because we said that there were 3 roots at, what point was it? -3, 0. So there was -3, 0. Ooh, we need to write. -3, 0 at a multiplicity of 3. Mult 3. Yikes, let me rewrite that. Mult 3. Forgot the L again. And then we had, I'm just going to change my color. No, I won't. 1, 0 was rational with a multiplicity of 1. Okay. And so, yeah, so that adds up to 4 right there. So 0 are imaginary, and none of them were rational. All right. Right. Example C, same things we've been doing. This one's a little bit crazy. There's a lot of numbers going on there, but right away, use the fundamental theorem of algebra. How many total roots are there? You should be able to say immediately there are 5 roots, because the highest degree is 5. How many are imaginary? We don't know yet. We need to graph it. One thing to keep in mind is it's giving us a window here. All right. So when you graph it, you need to reset your window to -10 less than or equal to x less than or equal to 10, -500 less than or equal to y less than or equal to 100. Okay. I'm using Desmos. So it's really easy. While you're home, you can use Desmos as well. Probably a good idea for you to get used to your graphing calculator. There's about 1 billion YouTube videos on how to use a graphing calculator, how to set the window, how to find the table. Okay, I'm not going to link to that. You're all capable of using YouTube. Type in the name of your TI-84, graphing. TI-84, setting the window. You can figure that out yourself. I'm just going to keep rolling with Desmos. Okay, so let's go over. Let's look at it. There you'll see that I've already got it up. Move my face. Okay. And then we have to reset the window. Real quick, I'm just going to check -10 to 10 for the x value. So Desmos, I do it over here. -10 to 10. -10. 10. And then the y value was -500 to 100. So -500 to 100. Okay. And look at that. That gives us a much better kind of view of what this graph actually looks like. Just by resetting that scale, we got to see the curve a little more. There's a lot of bends and twists in there. Okay, so let's look. Where does this cross the x-axis? Right away, I'm seeing this point, 4, 0. And I'm seeing right here, it looks like it bounces off the x-axis, the point -3, 0. What does that mean? Okay, so we've got some multiplicity here. Okay, multiplicity of at least 2 there. And we've got a multiplicity of 1 here. All right, now let's think about this. We said the degree was 5 for this, so there could be 5 zeros. That only adds up to 3. So there's 2 more zeros hanging out. It could be they're imaginary. Yeah, lots of times when you see twists and turns like this, you've got some imaginary roots going on somewhere. But without confirming that, and we don't know how to do that yet, I don't know. So it could be I have a multiplicity of 2 at -3, a multiplicity of 1 at 4, and then I just have 2 imaginaries, or 2 complex, I would say imaginary, roots hanging out somewhere. Or, that would be 5, right? Okay, 2 plus 1 plus 2 is 5. Or I could have a multiplicity of 4 here. So that's a multiplicity of 4. This is a multiplicity of 1. And I don't have imaginaries. That would add up to 5 as well, right? 4 plus 1 is 5. So really, it could be either of those things. And without actually getting through and solving the equations, which we'll do in the future, we don't know. So we have 2 options: multiplicity of 2 at -3, multiplicity of 1 at 4, and 2 imaginary roots for our 5, or multiplicity of 4 at -3, multiplicity of 1 at 4, and then no imaginary roots. Okay? It's kind of a lot. So let's go back to this. How many of those were imaginary? Well, okay, it could be 2. 2 question mark. All right. And if that's the case, we would have 3 rational roots. We'd have 1 at -3 with a multiplicity of 2. I'm going to just write M2 up here for multiplicity. We'd have 1 at, where was it? 4, positive 4, with a multiplicity of 1. Okay. No irrationals. Or, I was writing in purple. Or, okay, we had 0 imaginary numbers. We had -3 as a rational root with a multiplicity of 4, and 4 as a rational root with a multiplicity of 1. Okay, so we kind of have 2 options there. We have the green options where, okay, 2 imaginaries, 3 rationals, or we have the purple option where there was 0 imaginaries and 5 rationals. Okay, we'll learn more about that in future sections. All right. Go ahead and see if you can do this one on your own. Use the graphing calculator of your choice. That's Desmos. Okay, that's your actual TI-84, 83, whatever you've got. I recommend that. Go ahead and do it. When you hit pause, after you hit pause, after you hit play again, you're gonna see the answers. So definitely take your time. Don't hit play until you're ready. Hit pause now. All right. This has 3 roots, 0 of which are imaginary. And if we go look at the graph, we should see it bouncing off the x-axis because it's multiplicity of 2. You should see it bouncing off the x-axis as -4. Then we should see another root at -3. Let's go look. -4 and 3. Multiplicity of 2 for -4 and 1 for 3. Awesome. That's what the graph looks like. See how I actually left the window really crazy on this just because I think it shows the curves better. But yeah, there you go. All right. You should be free to do your assignment as found on your daily agenda or Google Classroom.